All right, so integration, remember, integration, integrating, integral, all of that means area under the curve. All of that, when you see any of that, when you see that word, integration, integral, all that means is area under the curve. Okay, so for example, F is a curve. I'll highlight it in yellow, in orange here. So F is that curve there. Right, that's the graph. Area under the curve is how much area from the function back down to the x-axis. Okay, so that's what we're doing. There's three ways to do it: using rectangles and trapezoids, which we did this week. Today I'm going to show you a different method, and then next week I'll show you. We've done antiderivatives, but like I said, there's a way to do antiderivatives. There's a way to find area under the curve using antiderivatives. We'll do that next week. Okay. All right. So first, all of these symbols here, I kind of color-coded and labeled it here. So I'll give you a second to label those. There's a meaning behind everything that you see. I told you about that dx part. Why do we write that dx part? Why is there that dx part? Today I'm going to explain why, what it means, and why it's important. Okay. So the first one is a limit. The first one is a limit. So if we make sure, so integration comes from a limit, okay? Just like derivatives comes from a limit. Everything derives from a limit. So the limit problem is integration, but they've changed that to look like what you see on the bottom. You're used to seeing what we see on the bottom here. But each part has an important piece in finding area under the curve, okay? So this part here, which we see as this part here, tells us how many rectangles do we need? How many rectangles do we need to find area under the curve, right? Just like we did a couple days ago. How many rectangles do we need? Okay? That tells us that. The middle part. That's the function. The function tells us the height. How tall are each of the rectangles? How tall are each of the rectangles? Because if I'm going to find area of rectangles, I need to know how many, and I need to know the length and the width. So this tells me the height or the length, right? And we write it as the function. That's job. And then the last part was the dx. The dx comes from the Greek symbol delta. Delta means change. How wide are each of the rectangles? How wide are each of the rectangles? So when we're finding area under the curve, width was very important of the rectangles, right? Because it was part of the formula that we did the other day. Without width, you can't find the area. That's why dx is important. It represents the width of each rectangle. Okay? The width of each rectangle. So that's why we always write dx. Because if we just write the function, you're just talking about height or length. Well, I can't find area under the curve. I can't find area of a rectangle without length and width. So that's where the dx comes in. Okay? That's why the dx is important to write every single time, because we're finding area under the curve. So this is what we're going to start doing. I'll come back in a second, but I want to kind of show you. The perfect way to find area under the curve is to make rectangles, just like we were doing, right? Just like we were doing earlier this week. But the perfect way to find area under the curve is to slice up those rectangles so thin that there is no overage. Because remember, sometimes we had some rectangles that went over, right? That went over. They were overestimates, right? Well, if we want to find area exactly, we don't want any overestimates. So the way to do that is to slice up the rectangle so thin that there is no overage. How many rectangles do we slice them up in? Infinite number of rectangles. If we had an infinite number of rectangles, we could slice them up so thin that it wouldn't go over. We wouldn't have a rectangle that goes over like this. Goes overage like that. Okay? That's where the formula comes from. That's where the formula comes from. So the total number of rectangles, you can see it says as the limit approaches infinity. Ideally, we'd want an infinite number of rectangles sliced up so thin that it fits that area, that blue stuff, perfectly. Okay? And that's where the equation comes from. So we read this as the integral of f of x from a to b. Okay? From a to b. A is the start of the interval. Where do we want to start from? Where do we want to end from? Okay? So for this guy, I want to start finding area at A and finish at B. I don't want to go past B. Okay, so those are our bounds. We call those bounds. The lower bound, I should put lower bound and upper bound. Lower bound, upper bound, lower bound and upper bound. Okay. Lower bound and upper bound. That tells us where exactly we want to start finding area and we want to finish finding area. Okay? So today we're going to use geometry. Geometry is shapes. We're going to start using shapes. Shapes that we recognize to find area. Okay? And that's what we're going to do today. So it's not going to be, we're not going to do a lot of calculating. We're not going to do a lot of, we're not going to do any antiderivatives today. We'll do that next week. Okay? So one of the ways to find area under the curve is by using shapes. Shapes that we recognize. So we can define the area under the curve for the function y equals f of x from a to b as an integral from a to b. Drawing a picture and using geometry is still a valid method of finding area. Sometimes that's the best method, easiest method. Okay? So for each, what I'm going to do is I'm going to draw a picture of what the function looks like. Okay? So remember, you have the integral. What color did I do? You have the integral, which has the bounds. You have the function, and then you have dx. Each of those serves a purpose, right? Okay, so what I'm going to focus on is the function right now. I'm going to draw a picture of the function. The function is 3. It goes from 2 to 9. So from 2 to 9. That's where our lower bound and our upper bound are. How do I draw the function? What is the function going to look like? What is the function 3 going to look like? Constant, right? So what does that look like? Yeah, it's going to definitely be constant. Yeah, just a horizontal line at 3. Horizontal line, no slope, because it's not increasing or decreasing. So we got 1, 2, 3. So just like that. I only care about the region from 2 to 9. That's the only region I care about because those are my bounds. So now what this question is asking is, what is the area under the curve? Well, that's a shape. It's a rectangle. It's a 7 by 3 rectangle. Base times height, length times width, whatever you want, 21. So the area under the curve is 21. Okay. Letter B. Last semester, I told you, anytime you see anything with an absolute bars, anytime in this class, anytime you see anything with absolute value, draw a picture. And that still continues. It's very hard to do derivatives, antiderivatives of absolute value. It gets too complicated. So the easiest way to deal with absolute values is by drawing a picture. Okay. Again, here's the function. Here are the bounds. Dx. So we're going to graph. So first of all, the bounds. The bounds go from -2 to +1. We're going to graph from -2 to +1. So at -2, where's the y value going to be for this guy? +2, right? Because the function is just absolute value. Absolute value, it's always positive, right? So when I plug in -2 in here, it's just going to be +2. So -2, +2. When I plug in -1, I get +1. When I plug in 0, I get 0. When I plug in +1, I get +1 again. And there are my bounds right there. So I'm going to connect the dots. So I have two regions. First one is here. Next one is here. So now I have to find area of those two. Well, they're shapes. They look like triangles. Area of a triangle is base times height divided by 2, or 1/2 base times height, either way. Well, I have two triangles. The first triangle has a base of 2, has a height of 2. 2 times 2 divided by 2, 2. The second triangle has a base of 1 and a height of 1. 1 times 1 divided by 2, 0.5. Add those two guys up. The area under the curve is 2.5. So anytime you have absolute value, they want you to find derivative of absolute value, area under the curve of absolute value. Draw a picture. Draw a picture, because it's so much easier than having to deal with trying to do other ways. More than likely, the picture is going to be some sort of V with absolute value. More than likely. That just creates triangles. Okay, that just creates triangles, which is easy to find area. Okay, so now we got a square root guy. Now we got a square root. So let's draw a picture. Next week, I'll show you how to use antiderivatives to do this problem. But for today, we'll just draw pictures. We'll draw a graph. So the bounds go from -3 to +3. Okay. So when I plug in, let's start with -3. When I plug in -3 in here, what am I going to get? Yeah, 0, right? So when I plug in -3, I get 0. Because -3 squared is 9. 9 minus 9 is 0. The square root of 0 is 0. So I'm going to go make a dot. 0. Okay, I'm going to skip -2 and -1 right now. I'm going to go to 0. And there's a reason why. I'll tell you in a second. So if I were to plug in 0, what would I get? If I were to plug in 0 here. 3. And then I'm going to skip ahead to 3. If I were to plug in 3, what would I get? No, 0. 0 again. Okay. So we have two options. It's either going to be another triangle, right? It's either going to be like that, or it could be a curved situation. I skipped -2 and -1 and 1 and 2 for a reason. I'm going to do that. Watch. I'll show you right now. Because for -2 and +2 and +1 and -1, we're not going to get a whole number. It's going to be a little bit. So we're going to have to approximate it a little bit. So let's say I plug in -2 here. When I square it, I get +4. 9 minus 4 is 5. The square root of 5 is close to what number? It's between 2 and 3, right? Closer to 2, but between 2 and 3. So I'm going to have to kind of use my imagination here. Or my, not imagination, but my best guess here. So what about when I plug in -1? Well, the square root of, -1 squared is 1. 9 minus 1 is 8. The square root of 8 is just under what number? 3. Just under 3. So what happens is, creates kind of a half circle kind of thing. And when I plug in 1, I'm still going to get close to 3. When I plug in 2, I'm going to get just above 2, just like I did on the other side. So what it's going to happen is it's going to create a what's called a semicircle, half circle. Area of a circle, pi times the radius squared. So what is radius of this guy? What's radius going to be for this circle? Yeah, it looks like the center is 0, 0. And to get to any edge, it looks like I'm going to have to go 3 units. So area equals pi times 3 squared. If you can't use a calculator, just leave it 9 pi. And you're, oh, sorry. I got to divide it by 2. Totally forgot about that because it's not a whole circle, right? It's a half circle, so I got to divide it by 2. So 9 pi over 2. Area of a half circle is pi times r squared over 2. That's the area under the curve. Now, is that the only way to find area under the curve for this problem? No. Next week, I'll show you a different way using antiderivatives. But for today, we're just kind of looking at shapes. Okay. All right. Okay, so now what happens if a function goes below the x-axis? None of our functions have gone below the x-axis, right? None of our functions. This guy did not go below the x-axis. These two guys did not go below the x-axis. The one on the front did not go below the x-axis. And if you look at the ones we've done before, the ones we've done to this point, none of them have gone below the x-axis up until this guy here. This guy goes below the x-axis. Well, how do I find area under the curve if it goes below the x-axis? And here's how we do it. So what happens if area is below the x-axis? Because if I were to go below, that goes forever, right? Above the x-axis just goes to the x-axis. So how do I find area for something below the x-axis? Is it going to go forever? The answer is no. Even though area is inherently positive, a Riemann sum and an integral can have negative values. So this is what's going to happen. If it goes below the x-axis, you shade up. If it's above the x-axis, you shade down. That's how to do it. Okay? So this guy here, they drew a picture for us. It's a semicircle and a piecewise linear. So a bunch of linears and a piecewise. And a linear and a semicircle. So they want to know what's the area under the curve from from negative 8 to positive 2. From negative 8 to positive 2. Okay. So the first thing I'm going to do is I'm going to shade. So negative 8 starts here. Positive 2 ends here. So let me shade the area that they want. So first of all, they want this area here under the curve, right? Under the curve up to 2. That area, the blue area, is going to be positive because it's above the x-axis. The other area, I'm going to have to shade up because it's below the x-axis. So I'm shading up to the x-axis. That area is going to be negative. Anything below the x-axis is negative. Shade up. If it's below the x-axis. Shade down if it's above the x-axis. And any area below the x-axis is negative. Okay, so we got a triangle. Looks like we have a triangle here. I have a pink, purple triangle here. So base from 4 to 8, it looks like it's 4. Height is from 0 to 8, negative 8, so that's going to be 8. Base times height divided by 2, so we get 16. But it's going to be negative 16 because it's below the x-axis. Any area below the x-axis will always be negative. So when you're finding area, picture it's positive, but the answer is going to be negative. Okay. Now this next part's kind of a weird, the blue part's kind of a weird looking shape. So I'm going to break it up into smaller. Hi, thank you. So what I'm going to do is first thing is a triangle here. There's a triangle here. So I'm going to find area of that little triangle. So it looks like that little triangle has a base of 2 and a height of 4. So base times height divided by 2, 8 divided by 2, positive 4. Okay. So now I got this little part left. The only part that's left is this little part here. Underneath that little half circle. They've said this is a half circle. So this is a half circle. Here's my question. So this is not even a calculus question. It's more of a geometry question, math 2 type question. How do I find area of the blue that's missing? Because that's not really a shape. Looks like a cutout of a shape.
Can you do a rectangle and then take out whatever the thing is for?
Yeah, exactly. That was my thought too. Picture it as a complete rectangle. Find the area of that. And then what's the shape of the missing white part? That's a half circle, right? So subtract the half circle. So find the area of the rectangle, subtract the half circle. That's what I was thinking too. Okay? So the area of the rectangle or square, I don't know what it is. It's actually a square. 4 by 4 is 16. So 4 by 4. So 16. And then I'm going to take away the half circle. The half circle, I'll highlight in a different color. I'll highlight in yellow. Oops. Okay. It's a half circle. They told us it's a semicircle. So it's going to be pi times the radius squared divided by 2. So all I got to do is find the radius of that guy. What's the radius of the yellow going to be? 2. So I have 16 minus 4 pi over 2. Well, 4 pi over 2 is just really can be reduced to 2 pi. So you're going to get 16 minus 2 pi. So the area of the blue is 16 minus 2 pi. Add up all of the regions. So I have the pink, purple, negative 16, right? I have the rectangle, the triangle that I first created, plus 4. And then I have that little part that I just found. That was positive 16 minus 2 pi. Combine like terms. Negative 16 plus 16 is going to be 0. So all I'll have left is 4 minus 2 pi. They're not like terms, so you're done. The area of all area under the curve is 4 minus 2 pi. Okay. All right. Okay, so now, similar problem. So we have a function, 3 minus x. First thing to do is we need to sketch that graph. We're going to go from 4 to 8. So I want you to sketch that graph from 4 to 8. Where is it? Where does it go? Sketch that graph from 4 to 8. 3 minus x. That's the function, 3 minus x. So I'll give you a hint. It's going to be a line. Okay, so when I plug in 4, I get negative 1. 4, negative 1. When I plug in 5, I get negative 2. When I plug in 6, I get negative 3. When I plug in 7, I get negative 4. When I plug in 8, I get negative 5. Under the curve, under the x-axis. Under the x-axis means it's going to be negative. Okay, so my answer is going to be negative. Well, what shape does that look like? Looks like a trapezoid, right? Looks like a trapezoid. You have base 1 and base 2, or the opposite, doesn't matter. And then you have the height. So we got 1 here. I got 5 here. So area of a trapezoid is base 1 plus base 2 divided by 2 times the height. It's on its side, so the height's going to be 4. 6 divided by 2 is 3 times 4 is 12. And then it'll be negative 12, yeah. Exactly. It's going to be negative 12 because it's underneath. We find the area like it's positive, and then you throw a negative in there because it's under the x-axis. Yep, very important. Because if we have area that's negative, that means it has to be under. B, what's B asking? What's the question for B asking? What's the difference between A and B? The questions they're asking. It's kind of a trick question. The difference is nothing. A and B are asking the same exact question. One's in words, one's in mathematical symbols, whatever you want to say, integral symbols. They're asking the same exact question. Because remember, these are your bounds. This is your function. So they're just asking how much area is made in that region. What's the area under the curve? That's all it's asking there. It's the same thing as A, just in words. A is in words, B is not. Okay. Okay. Let's see, we might be able to finish there. Okay, so let's throw in one trick. Okay. So they've told us that the area under the curve for the sine function, the sine wave. So let me draw a picture of the sine of sine. Let me see. Let me draw it right here. So one phase, one cycle, I should say, of the sine. Let's see, -1, +1. We got pi over 2. We got pi, 3 pi over 2, and 2 pi. So when we draw sine, the sine wave, it starts at 0. At pi over 2, it becomes 1. At pi, it becomes 0 again. 3 pi over 2 becomes -1. So the sine wave kind of looks like this. That's what the sine wave looks like. So what they have told us is that if you find area under the curve from 0 to pi, 0 to pi, 0 to pi is right here. If you find that area, they're telling you right now it's going to be 2. That's what they've given us. So knowing that, what's going to be the area from pi to 2 pi? In other words, this part right here. It's going to be -2. Yeah, how do we know it's going to be -2? You're absolutely right. It's going to be -2. How do we know? Because it's the same values, right? All of these, if we were to look on our charts, all of these values here on our charts repeat over here. They're just negative, right? It's just the opposite values. From our chart, we know that. So that means it's going to create the same area just below the x-axis. So that means the area under the curve here is -2. What would the area under the curve be from 0 to 2 pi? Yeah, the whole phase, right? A whole cycle would be 0 because you would have to add up 2 and -2. Actually, let me move this down here. Okay. What would it be from 0 to pi over 2? It would be here, right? Again, those are symmetrical. This is symmetrical. It doesn't look symmetrical the way I drew it, but it is actually symmetrical. Right? So it would be 1. Okay. So let me... Okay, last 2. D, what does D do? D is from -pi to +pi. So now I need to end at pi and begin at -pi. So what is D really doing? It's just shifting it. It's just shifting it down. It's saying instead of ending at 2 pi, you're going to shift it over and end there. And then instead of starting at 0, you're going to end at -pi. Because the distance from -pi to +pi is 2 pi. The distance from here is still 2 pi. So knowing that is just a shift, what are we going to get? 0, the same answer we got for B. It's just a shift. This guy is shifting that way pi units. Okay. Last one. So this one only goes from 0 to pi. So it's half of it. But where is it different? It's got the +2, right? It's got a 2 with it. There's a couple different ways you can do this. Have we done the? We haven't done the properties yet, so I can. What does the 2 mean to a function? What is that going to do to the picture, to the graph, when I put a 2 there? It's going to shift everything up 2 units. It's going to shift everything that you see, every dot that you see, every blue dot that you see, it's going to shift it up 2 units. So this blue dot here will no longer be there. It'll be at 2. This blue dot here will no longer be there. It'll be at 3. This blue dot here will no longer be there. It'll be at 2. This blue dot here will no longer be at -1. It'll be at +1. Okay? That's what it's going to do. How do we figure that out? Or how do I do that? This is how you do it. Actually, we have talked about this. When we talked about antiderivatives last week, one of the properties was this guy here. We'll talk more about this next week too, but if you're adding or subtracting 2 things, you can give them each their own. And you can break it up into 2 smaller problems. That's what I'm going to do here. So I'm going to give that one a problem. And I'm going to give this one a problem. By doing it that way, I know the answer to one of them. Wasn't this one of my questions earlier? 0 to pi? What did I get for that answer? It actually wasn't a question, it was the given part, right? That was given. That's just 2. How do I do this one? I'll give you a hint. You did it earlier. We did it earlier. The very first one we did, the constant, right? 3, right? Draw a picture. So let's draw a picture. From 0 to pi, the function is 2, right? Looks like a rectangle. The width or the length is pi. The height or the length or the width is 2 pi. And there you go. Okay. So just drawing shapes. Just drawing shapes, drawing figures to do it. That's another way. It's a nice way because it's not really calculus. It's more just drawing shapes and finding areas. Whenever you can do that, do it because it's nice. The bottom part is just if you wanted to do on a TI, if you wanted to find area under the curve, this is how to do it. Directions, that's it. Okay, I just threw it on there just in case. So you have it for reference. Okay. All right. Okay, so Monday, I'll give you the practice assignment. And that's about it.